Let's consider now the osmotic pressure. To understand the osmotic pressure, let's consider a container with, say, water, some liquid in it, and we have this divider here in the container, and this divider will allow water to flow back and forth. And due to gravity, since water can flow through the divider, then the level on each side of the divider will be the same. We have air sitting on top of the liquid, and so it's exerting an air pressure, and the air pressure is the same on either side of the divider. And so due to the air pressure and gravity, the level of the liquid will be constant across the container. Now, let's say we take a piston and we put it on top of the liquid on one side of the divider, and we put weights on top of the piston. So we're going to put these lead blocks, lead bricks on top of the piston. So now we have more pressure sitting on top of the liquid in the right side, and so this piston is going to drop, and the level on the right side of the liquid will rise. We'll still have air sitting here. So now we'll have a disparity in the levels of the two liquids on either side of the divider. Because of the weights we put on the right side, water's been forced through this divider into the left side, and so it's not until the air pressure plus this additional weight of the water due to gravity is equal to the air pressure and the weight of these lead bricks. So when the weight of the air and the lead bricks is equal to the air and this additional amount of water are equal, then the level will stop rising on the left side. But we'll have a disparity of levels on the left and right side. And if we calculated how much pressure would be required to create this height, this additional height in the water level, so we'll call this delta H, the additional height. And if we calculated the pressure required to push up this additional height, that's called the osmotic pressure. So it's the pressure required to raise the water level delta H amount. So this is called the osmotic pressure. Now, the equation for the osmotic pressure is fairly simple. It's pi, we call this the osmotic pressure, is equal to the molarity of the solution times the ideal gas constant times the temperature of the solution. So this is the osmotic pressure. This is the molarity of the solution. This is the ideal gas constant. And this is the temperature in Kelvin, because the ideal gas constant has units of Kelvin for temperature. So if we know the molarity of the solution and the temperature, we can calculate the osmotic pressure. Now, how this works for a solution is as follows. So we have our container with our water level in it. And we put in a divider again. And this divider will allow water to flow back and forth. And so now let's say we put a solute in our solution. So say we have sugar. And we put sugar in the right side, but not the left side of the container. And this porous divider allows water to travel through it, but it will not allow the solute to travel through it. So the sugar is stuck on the right side of the container only. It can't get to the left side. So what happens is we create an osmotic pressure because the concentrations want to be the same on both sides of this divider. So here we have a sugar solution, here we have pure water. So water will flow from left to right to try to dilute this sugar concentration so that it would match pure water. And so water will flow to the right side until the osmotic pressure is reached, at which point the water will stop flowing. So what will happen is we'll have water flowing to the right side, so the water level on the right side will increase. And then when this weight of the water right here, weight of water equals the osmotic pressure, then water will stop flowing. So it's just like we had put the weight on the left side and forced the water down through the divider from left to right. So this is the osmotic pressure of the solution. The osmotic pressure is given the letter capital pi, is the molarity of the sugar solution times the ideal gas constant times the temperature. So let's calculate the osmotic pressure. Say we have a 0.1 molar sugar solution at 25 degrees centigrade. Let's calculate the osmotic pressure. So the osmotic pressure would be 0.1 molar. So molar is moles per liter for its units. Have the ideal gas constant. And then the temperature, 25 degrees centigrade, is 298 Kelvin. So you can see that liters will cancel, moles will cancel, Kelvin will cancel. The only unit left is atmospheres, so that's the unit for osmotic pressure. So this gives an osmotic pressure of 2.4 atmospheres. So if we had 1 atmosphere of air pressure sitting on top of this liquid, the osmotic pressure would be raised to 2.4 atmospheres. That's over doubling the pressure. So you can see how for a solution that's not very concentrated, the osmotic pressure has a large response. Now, if we had a salt solution like sodium chloride, again, the osmotic pressure depends upon only the molarity of the solute particles. And so if we have a salt solution, we would use the Van Hoff factor, I. So if we had sodium chloride instead of sugar here, I would be 2. If we had magnesium chloride, I would be 3. So remember to take into account the dissociation of the solute when it dissolves and the solution is formed. So if we had a 0.1 molar salt solution, then the osmotic pressure would be 2, because of sodium chloride breaks up into 2 separate particles, sodium plus and chlorine minus. Then we have 0.1 molar sodium chloride solution, and then the ideal gas constant. And the temperature. And so this would just equal to double this. So this would be equal to 4.8 atmospheres. So if we have just a 0.1 molar sodium chloride solution, the osmotic pressure will be 4.8 atmospheres. So since the osmotic pressure has such a large response to a small concentration, one thing that's useful is to be able to measure molecular weight using osmotic pressure. So if we have our osmotic pressure equation, M is the molarity, so this is the moles of the solute divided by liters of the solution. And we can write moles of the solute as the grams of the solute divided by the molecular weight of the solute. So this is moles of solute, then we divide again by liters of solution times RT. So this is the osmotic pressure. So if we measure certain grams of solute, put it in a certain liter of solution, and we know the temperature, we can calculate the molecular weight. So just solving this for molecular weight, I get grams of solute divided by the osmotic pressure times liters of solution times RT. So if I measure out a certain number of grams of solute, dissolve it in a certain liter of solution, measure the osmotic pressure experimentally, which is easy to do, and know the temperature, then I can calculate the molecular weight of my solute. So this is useful for polymers. When it's hard to measure the molecular weight of a large polymer, it can be done through the osmotic pressure. And this is how it's done in industry. Say we have 28 milligrams of a polymer, and we dissolve that in 25 milliliters of solution. We measure the osmotic pressure. The osmotic pressure is 3.2 torr at 25 degrees centigrade. Let's find the molecular weight of our polymer. So we can use this expression that we derived. So the molecular weight is equal to the grams of solute, which is 28 milligrams, divided by the osmotic pressure, and liters of solution. So we have everything we need. So we'll calculate the molecular weight. Grams of solute, 28 milligrams. So this is 28 times 10 to the third grams. And then divided by the osmotic pressure, so 3.2 torr. But R, the ideal gas constant, is given in terms of atmospheres, so I'll convert this to atmospheres. So there's 1 atmosphere per 760 torr. So that's the osmotic pressure. Now the liters of solution, so that's 25 milliliters, so that's 0.025 liters. And then multiply by R. And the temperature, 298 Kelvin. So we'll go with our units. Atmospheres cancels, liters cancels, Kelvin cancels, and we're left as grams per mole. And we want to know the molecular weight, so that's grams per mole. So the molecular weight of our polymer is equal to 6,500 grams per mole for our polymer.